Hi friends, welcome back to the channel. Today we are going to solve a problem from the topic of solid mechanics. This is a fairly easy problem, but while solving this, I would like to tell you a few things about Mohr circle and certain things that you often overlook when you start working with Mohr circle or start solving problems related to Mohr circle. So coming back to the problem, they are saying we have a critical point in a component. The state of stress is shown over here. We have sigma x, sigma y, sigma xy and sigma yx. They are both equal. That comes out of your angular momentum balance or momentum balance. Uh, all other stress components are zero. The yield strength of the material is given. They are asking us to figure out the factor of safety on basis of maximum shear stress theory. So the first question is this a general 3D state of stress problem, or can we reduce the problem from 3D to, let's say, 1D or 2D? Can we do that? The answer is yes, we can convert the problem from 3D to 2D because we have only in plane stresses, or this is equivalent to that of a plane stress condition. There is no stress component in the z direction. Make sense? So I can invoke the Tresca criteria or the maximum shear stress criteria for the plane stress condition. So to invoke this maximum shear stress theory, I should first find out the principal stresses in the three direction corresponding to this critical point. Let me call them sigma 1, sigma 2 and sigma 3. Then I should arrange them in a particular order, and then I should evaluate my maximum shear stress, which will be sigma 1 minus sigma 3 by 2, then compare it with respect to my shear strength, not yield strength of the material, but shear strength of the material. So that's the procedure we are going to take to solve this problem. And where does Mohr circle comes into picture? We know the general state of stress, so Mohr circle helps us to evaluate these three quantities. Apologies for my poor sketch. I'm not that good in sketching things, but let me drive home a few key concepts related to Mohr circle. So Mohr circle comes handy when you want to evaluate the normal and the shear stresses at a plane inclined to your normal Cartesian system. To explain it further, let's say I know the state of stress at a point in terms of sigma xs, sigma yy and tau xy. Plane stress condition. Now I wanted to know what is the state of stress, or what is a normal stress and the shear stress if I consider a plane like this whose normal is inclined at theta degree to the x-axis. You would ask me as an engineer, hey man, can you cite an example where we actually get to solve this kind of problems, or where we kind of ask ourselves, hey, what is a normal stress that is acting along this plane and what is a shear stress that is acting along the plane? One example, let me take you to one example. What I have shown over here is an edge crack on a finite width plate which is subjected to tensile load. This is an edge crack. This is a problem from the topic called fracture mechanics, but you don't have to worry about that. But when we do problems in fracture mechanics, the question arises is, hey, what is the component of stress that tries to open up this crack? So what I'm trying to do is, hey, what is the stress, normal stress along this direction? Let me call that directions m prime, m prime. Then I will call this direction as n prime. So what is the component of stress along this direction, which is sigma m prime m prime, that tries to open up the crack. Then I can ask, what is the component of stress which acts along the plane of the crack? That's another question I can ask. So these are application in mechanics where we actually use stress transformation laws. Okay, so that's where stress transformation laws comes handy. Now coming back to Mohr circle, I so there are problems where we actually want to evaluate the normal stress perpendicular to a direction or acting on a plane, and also there are situations where we need to compute the component of stress that acts along the plane. So there are requirements, there are applications. Uh, Now coming back to Mohr circle, the first thing you should remember about Mohr circle is the axis or the sign convention. What I like to do is I follow the sign conventions as mentioned, as specified in the book of Timoshenko. So I have my tau x1 y1 axis coming down and sigma x1 axis going towards the right. Key thing is, see this, I'm plotting tau x1 y1 here. I'm not plotting tau y1 x1, because what happens is once you start creating your Mohr circle, the first thing you do is, if you know the stresses in this coordinate system, in this xy coordinate system, if you know the stresses, what you do is, as a first step, you will try to figure out where is my point A, or where is this plane in my Mohr circle. So this is defined by 2 points, sigma xx and tau xy. See, tau xy is positive in this sense because this is my positive x phase and my tau xy is acting along the positive y direction. So it is obviously positive. That's why I have marked that point A along the positive tau x1 y1 axis. Once we come to this plane or representing point B on the Mohr circle, see, it's like I have rotated my axes. Now my axes are like this. Little x1 is pointing up and then little y1 is pointing like this. But still my stresses are not changed in their direction. They are still acting. My sigma yy is acting like this, and then my tau yx is still acting like this, isn't it? Yeah, my tau yx is acting like this. But I'm trying to plot tau x1 y1. The positive direction of tau x1 y1 is this way around, but my tau yx is pointing the other way. That's the reason why point B falls on this quadrant where your tau x1 y1 is negative. Now you have 2 points, fairly easy to construct a circle now. Is it fairly easy to construct a circle with 2 points? Not necessarily. You cannot construct a circle with just 2 points. So what you need more is the center. The center is well defined. If you know both the sigma xs and sigma yy, the center is sigma xs plus sigma yy by 2. So this point, I didn't mark this there. It gets a bit cluttery, but let me mark it. Now, where does this fellow lie on the Mohr circle? We know this plane is attained after rotating, or we know this plane is at an inclination of angle theta from the x-axis. In Mohr circle, in order to get that point, we need to rotate by an angle 2 theta. So here it is theta, but here it is 2 theta. Similarly, here this face was at 90 degree with respect to this face, But on the Mohr circle, those two faces are 180-degree apart. So these are the few things which you need to keep in mind uh, when you work with uh, Mohr circle. And the equation that governs the Mohr circle is these two expressions. I wouldn't ask you to memorize these two equations because that's not the way how it should be done. Just remember how it is drawn and all those things. I wouldn't ask you to memorize these two equations. And why a theta inclination corresponds to a rotation of 2 theta? The reason is here because the argument of all these cos and sine terms is 2 theta, not theta. That's the reason why 90-degree faces are 180-degree apart in Mohr circle. Finally, we have expressions for the principal stresses, which is simply the center plus the radius, center minus the radius is the second principal stress. I think it was a lengthy discussion on Mohr circle, but I think it was worth. Now let's get back to the problem and solve it. One final bit of information before I round off that discussion on Mohr circle. I would like to show you the expression for the principal stresses. This is something you should know because in exams I have seen these people ask questions where you need to invoke these equations and where you have to plug in these numbers. One bit of information is this quantity is the radius of the Mohr circle, okay, and this is the x coordinate of the center. That's one way how you can remember this expression rather than just simply mugging it up. So by using those two formula I can arrive at an expression for the first two principal stresses. What about the next one? So in a plane stress problem, the third principal stress is always 0. Why is it so? I won't get into the details, but see, strictly speaking, principal stresses are the eigenvalues of your stress tensor. When you have a plane stress problem, what happens is your stress tensor or your stress matrix looks something like this. You have a lot of zeros there. If you are good at matrix algebra, then you know one eigenvalue of this matrix should be 0. Why? Because product of your eigenvalues is equal to the determinant of the matrix. Once I take the determinant of this matrix, it turns out to be 0, which essentially means that one of the principal eigenvalues of the system should be 0. One principal eigenvalue is same as that of the principal stress, so one principal stress should be 0 when you have a plane stress problem, but the other two principal stresses can be evaluated using Mohr circle. So here I evaluated all the three principal stresses. Now I have arranged them and I evaluate the maximum shear stress acting at that particular point. They said it's a critical point, so the maximum shear stress at that point is 130 MPa. Makes sense? And we are not bothered about the orientation. It may be acting along a plane, but we don't know the orientation of the plane. But in order to invoke Tresca criterion, we don't need that. Then we bring in this assumption. It's not an assumption because they say Tresca criterion holds true. Then you can say that if my tensile yield strength is 468, then my shear yield strength is 234 MPa. Now they are asking us to evaluate the factor of safety. So factor of safety is nothing but the shear strength is the ratio of shear strength to shear stress. In this case, it comes out to be something like 1.8. One thing I like this analogy all the time. Strength is something like the amount of water that a particular glass or beaker can hold. Let's say this is of 1 liter, then the capacity or the strength of the material can be thought of as 1 liter, the maximum it can hold. And the same beaker, now I am pouring only half a liter, it can be thought of the stress that the particular structure is subjected to. When this is the condition, we still have a factor of safety of 2, because half of the beaker is still available to us to fill further and further. So whenever we talk about strength and stress, this is a good analogy to think about the beaker and the capacity and the original volume or of the liquid present in the container. This is a good analogy to keep in mind. So this was an easy problem, but the key concept what I wanted to drive home is the concept of Mohr circle and the small nitty-gritties of Mohr circle where you can get it wrong. So those were the things what I wanted to drive home. Otherwise, it was a very simple problem where all the quantities were given and all we had to do was just plug and check. Thanks for watching.